The modern odor has been a major problem for pulp and paper mills. The modern efficient pulp and paper mill has relatively few problems with adverse environmental impacts, since wasteful practices are minimized and chemicals were based upon end-of-pipe treatment, with little regard for preventing the generation of pollutants in the first place. Industry managers, federal and state regulators, and environmental organizations now recognize that pollution prevention with recycling and reuse is the more effective path to protecting human health and the environment. In the simplest terms, if you don't generate pollutants in the first place, you don't have to handle them later. Odor has been a major problem for pulp and paper mills, but significant advancements have been achieved. Most odors from kraft pulp mills are a result of reduced sulfur compounds emitted into the air in low concentrations. Although these chemicals are not dangerous in the amounts found in mill emissions, they certainly are unpleasant to smell. Unfortunately, humans can detect reduced sulfur odors even at concentrations of as little as 1 part per billion, so eliminating the odor is no easy task. Reduced sulfur compounds are formed due to the use of sodium sulfide as one of the chemicals for cooking wood chips. Reduced sulfur compounds can be found in vent gases from many sources in pulp mill and chemical recovery areas, such as digesters, evaporators, turpentine, and tall oil recovery. Nowadays, gases from digester and evaporator systems are routinely collected and then incinerated in power boilers, lime kilns, or thermal oxidizers to convert the reduced sulfur compounds to odorless salts. The low-odor recovery furnace, black liquor oxidation systems, and non-contact evaporators have significantly reduced odors from this step in the pulping process. Steam stripping of condensed vapors from digesters and evaporators, with subsequent incineration of the stripped gases, is also used to minimize reduced sulfur emissions. Today, the North American pulp and paper industry produces 25 million more tons of kraft pulp per year than it did in the 1970s. But the associated odor compounds per ton have actually dropped by as much as 95%. But why use sulfur at all? Sodium sulfide is a key component of the kraft process and plays a vital role in protecting the cellulose against degradation in the cooking process. The kraft process produces very strong pulp, and this strength is important in many consumer products from corrugated boxes to copy paper. The black liquor that is burned to recycle the cooking chemicals also generates energy, so the kraft pulp mill uses the least externally provided energy, that is, the least fossil fuel, of all pulping processes. Air pollution also consists of solid particulates. Scrubbers, electrostatic precipitators, mechanical collectors, and fabric filters have been developed to remove solid particles emitted to the atmosphere. Development of air emissions measuring and monitoring devices has advanced the industry's understanding of the relationship between operating variables and emissions from process equipment. Electrostatic precipitators are the predominant particulate removal devices used by the pulp and paper industry for recovery furnaces and lime kilns. In the electrostatic precipitator, a high voltage creates a negatively charged field through which the dust-laden gas passes. The particles collect the negative charge and are drawn out of the airstream as they pass by positively charged plates. The plates are periodically wrapped by mechanical action, causing the particles to fall into hoppers. Electrostatic precipitators typically remove 99.9% by mass of the dust particles input to the system. Fly ash removed by electrostatic precipitators on kraft recovery furnaces is recycled to the black liquor process stream. This conserves chemicals, reduces cost, and prevents pollution. Scrubbers are either wet or dry type devices that scrub a gas stream of pollutants. Wet scrubbers remove dust and gaseous contaminants from a hot, moist gas stream using a suitable wetting liquid, usually water. Dry scrubbers perform the same function, using a moving bed of granular filter instead of wetting liquid. Mechanical collectors are the simplest type of particulate removal devices. They operate by forcing the gases along paths that the particulate cannot follow, and so the material drops out of the gas stream for collection. Mechanical collectors, such as the cyclone separator, are limited to the removal of relatively large particles. An efficient device for collecting fine particulate matter is the fabric filter or bag house. Cylindrical cloth bags of fine mesh strain the particles from the gas stream passed through them, much like a household vacuum cleaner. The pulp and paper industry has made major progress in wastewater pollution control. Two commonly measured water pollutants are biochemical oxygen demand, or BOD, and total suspended solids, or TSS. BOD is material that depletes the oxygen available to fish and other organisms in lakes and streams. TSS are materials that cloud the water. Other pollutants found in processed wastewater include pH-altering substances, oil and grease, ammonia, nitrogen, phosphorus, chlorinated organic compounds, and substances that alter the color of the water. During the past 40 years, the North American pulp and paper industry has reduced wastewater discharges per unit of production by 95% for BOD and by 80% for TSS. Water use and effluent flow rates also continue to decrease. It now takes 70% less water to make a ton of paper than it did in 1959, the basis year of the first survey of water use. Treatment of wastewater or effluent from the pulp and paper mill usually takes place in two stages. The primary clarifier removes suspended solids from mill effluents by gravity settling or flotation. The secondary treatment removes oxygen-depleting dissolved solids and chlorinated organics. The primary treatment removes suspended solids, portions of which are oxygen-depleting substances and toxic to fish and other organisms. Relatively large floating or suspended particles from an effluent stream are generally removed by gravity settling. Gravity settling is carried out in a large circular clarifier. The clarifier is designed to provide sufficient retention time for the solids to settle to the bottom of the clarifier. The settled solids are then raked toward a center sump by means of a center-mounted sludge scraper. The solids are then dewatered and may be burned in a furnace for energy recovery or deposited in a landfill. The increasing cost of landfill is an economic incentive for mills to reduce their solids discharge and find other means of disposing the sludge. One way is by land spreading. Land spreading utilizes the nutrient-rich sludge as fertilizer for agriculture and horticultural uses. Some sludge is being used to create products such as asphalt, roofing felt, and animal bedding. Secondary or biological treatment is usually performed under aerobic conditions, that is, with oxygen. Microorganisms, mostly bacteria, convert organic waste into carbon dioxide and water. Because the microorganisms require oxygen, sufficient air must be supplied. The aerated stabilization method mixes air with the effluent. In some instances, additional nutrient chemicals containing nitrogen and phosphorus must be added to stimulate metabolic activity. This bioconversion is capable of converting 30 to 70% of the BOD measured organics into insoluble material. As the food supply becomes more limited, the rate of bioconversion slows down. When the food supply is depleted, the microorganisms settle out of the treated water and form a sludge, which is separated from the clarified water. The activated sludge system is another popular high-rate method of secondary effluent treatment. It requires less land area than the aerated stabilization method. The activated sludge system uses a microbiological flock held in suspension in an aeration tank or mixing chamber. The tank size is dependent on the amount of effluent to be treated. Primary clarified effluent is continuously fed into the tank, and the activated sludge solids multiply as dissolved organic waste is metabolized. At the same time, effluent is continuously drawn off to a clarification unit where solids are separated. A certain portion of these solids are recirculated back to the aeration tank to maintain a high flock density, while the remainder is concentrated and disposed of along with the primary sludge. Tertiary treatment is sometimes used to remove the pulp mill effluent color. The tannin and lignin derivatives responsible for the brown color are slow to biodegrade and are usually unaffected by conventional secondary treatment methods. Tertiary treatments for the removal of the coloration include utilizing lime, alum, or polymer coagulation, membrane processes, activated carbon absorption, and filtration through soil substrata, which is also known as rapid infiltration. These treatments are capable of providing varying degrees of color removal. Dioxin is the common term for a chlorinated organic compound that has 96 different molecular arrangements, called congeners, some of which are mildly or even highly toxic. Dioxin was first discovered in the effluent from pulp mills in 1985, and studies confirmed that the use of elemental chlorine to bleach wood pulp was producing small amounts of dioxin byproducts in the mill wastewaters. Pulp mills in North America have revised their bleaching processes to either become ECF, that is elemental chlorine-free, or TCF, totally chlorine-free. The bleaching sequence shown here is TCF, since there's no chlorine in any form used. The EPA reports that dioxin is now at undetectable levels in almost all paper industry wastewater discharges, even using today's highly sophisticated analytical techniques. The pulp and paper industry has been actively engaged in pollution control for many decades, spurred by economic considerations as well as regulatory legislation. In the 1970s, there was a marked increase in federal legislation to provide a national environmental framework, which has continued into the present. There's been a 300% increase in the volume of U.S. federal environmental laws since the early 1980s. Several environmental laws establish a federal-state partnership. The federal statute sets the framework and minimum standards, while the state agencies prepare the permits and apply the regulations to the various regulated manufacturing facilities. State laws and even local ordinances play an increasingly important role in the regulatory context for modern pulp and paper mill operations. Sometimes a state may be implementing a federal regulation, or the state may have its own laws and regulations, which differ from or even conflict with federal requirements. Many of these statutes and regulations require that pulp and paper mills obtain permits from federal and state authorities. The permit is like a contract, describing how applicable laws and regulations will be carried out at the mill. Typically, there are detailed provisions describing how compliance will be measured. The regulations impose strict civil and even criminal penalties for failure to meet these requirements. During the last 10 years, federal and state regulators have undertaken cooperative programs with individual pulp and paper mills to support in-process pollution prevention and reuse efforts that have resulted in air and water emissions significantly below the permitted levels. Where is the industry headed environmentally? In 1994, this minimum environmental impact mill, which has a closed-loop production process, isn't here yet, but it's an increasingly realistic goal. The minimum impact mill would have efficient production processes with minimum water consumption and minimum waste generation and disposal. The first steps involve conservation of fresh water. Water conservation has improved by more than 40% since the mid-1970s. In fact, some recycled board mills have achieved complete closure of the water systems, but this level of closure is not possible for many grades of paper. Methods such as closing whitewater systems and screen rooms, instituting spill capture and recovery systems, reclaiming and reusing cooling water, and treating and recycling evaporator condensate have significantly decreased both freshwater usage and wastewater discharge for many mills. Protecting the environment is a difficult challenge, but the final answer is to prevent the generation of pollution in the first place, not to handle it at the end of the pipe. By optimizing fiber, chemical, and other raw material usage, the industry is minimizing waste generation and unwanted environmental discharge. A good example of this approach is the recent modernization of pulp bleaching operations to ECF or TCF bleaching. Improved processes reuse and recycle chemicals and other byproducts within the papermaking system and in the creation of marketable goods. While the environmental problems that once plagued the paper industry have largely been solved, there's still a lot of work ahead before the industry can say it has no environmental impact. But we're getting closer, a lot closer in recent years, to that goal. Remember, we are all stewards of the future. This is the end of the lesson. Click on a selection from the main menu on the left.